Hi everyone. So today we're going to be talking about congruent arcs and chords of circles. So yesterday in our last lesson we talked about arcs of circles. Now we're going to talk about congruency. So theorem number one, in the same circle or in congruent circles, congruent arcs have congruent chords. Okay, so that means that if I have an arc here, A, B, and an arc here, C, D. So these are arcs. If I mark those arcs congruent to each other, then the chords that connect those arcs, so chord here and chord here, then they would also have to be congruent to each other. Now they're not, obviously they're different lengths in terms of the arc versus the chord, but the two chords would be equal and the two arcs would be equal. And the converse of that would then also be true. Congruent chords then would have congruent arcs. So if I note that this is 2 and this is 20 degrees and this is 2, well then if these two chords are of length 2 and equal, then this would also then have to be 20 degrees. So we're going to use that a lot. It's a very helpful theorem. This actually leads us to two others. Now again, we will be investigating why these work in class, but a diameter that is perpendicular to a chord bisects the chord in the arc. So let me show you what a picture of that would look like. So I'm going to draw a diameter actually going straight down. Now I know it's a diameter if there's a dot in the middle, and I'll call this circle R. If there's a chord like this, and that angle right there is right, it makes the chord and the diameter perpendicular to each other. So therefore, this segment would be bisected and this segment would be bisected. Now, the reason that is because if I were to take this center and just draw lines to the end points of the chord, I want you to recognize then these guys would be equal because they're radiuses, which would create an isosceles triangle. And we know that if we have a perpendicular going through, if we have an altitude going through the vertex, then it actually becomes a perpendicular bisector, therefore bisecting the segment, and then therefore the chord from this theorem. All right, and the last theorem we're going to talk about is that in the same circle or in congruent circles, chords that are equally distant, which means equidistant, okay, so equally distant from the center are congruent. Equally distant from the center are congruent. Congruent chords then are equally distant from the center. All right, let me show you what that might look like on a picture. So we have a chord maybe like this, and a chord maybe like this, and I have that, and I have them both equally distant from the center. That would make these two chords right here, it would make them that they were equal. And that should kind of make sense to you. If I'm the same distance away from the center of the circle, then they'd have to be equal. All right, so let's look at some examples of this. All right, so here's our first example. I look at this and I see that the diameter is perpendicular to the chord. So I first know that it's bisecting the chord. So I know that x and y are equal, but I have to figure out a way to find their value. Well, you might notice that this right here is actually a radius, and the radius is 13. So I'm going to use that and draw a line, a radius from that center to the end of the chord, and I'll label it 13 because we know all radiuses are equal. Now let me pull that triangle out now. So now I have a right triangle with a side 5 and a side 13, and I'm going to try and find y. To do that, I can either use one of two things. I can use the Pythagorean theorem because Pythagoras is always our friend if we have a right triangle and two sides given. So 25 plus y squared equals 169, and subtract 25 from both sides by balancing the equation. Y squared equals 144, and then we take the square root of both sides. Remembering that when we take the square root, we always have a positive and negative answer. but in this case, we only have to look at the positive answer because it is a length. Now, that's one way. The other way would be for you to remember your Pythagorean triple, 5, 12, 13. And because 13 is the hypotenuse of this, then we are allowed to say that y is equal to 12 with no work needed. Again, there's that place that Pythagorean triple is helping us. So y is 12 and x is 12. Okay, again, remember, use the radiuses to create triangles. All right, here's another one. I see that I'm trying to find the value of x and y. Well, I see that these chords are congruent, so I already know that, that this arc and this arc are equal. So I know that whole arc is 86 degrees over here. But I see a diameter that's perpendicular to a chord, which means that it's bisecting the chord, which makes x 5. But if it's bisecting the chord, it's also bisecting the arc, which makes y 43 degrees. All right, here we go. I'm trying to find x, y, and the measure of angle arc AB. Well, I can see the 60-degree angle, and 60 and a right triangle? Oh my goodness gracious, that should start to get me thinking. I have a 30, 60, 90 triangle with this radius, or the hypotenuse, of 6. So remember, you always want to work your way back to the short leg. So if the hypotenuse is 6, the short leg across from 30 would have to be 3. And that would make the side opposite 60 3 root 3. So then x is 3 root 3 and y is 3. But it also wants the measure of arc AB. And since this is a radius is, if I just extend, is also a diameter, is part of a diameter, which means that I can use the theorem that a diameter that's perpendicular to a chord bisects the chord and the arc. So if this central angle here that we learned about last lesson is 60 degrees, it makes this arc 60 degrees, which makes this arc 60 degrees. So the measure of arc AB would then have to be 120 degrees. Definitely one that you could pause and rewatch. All right, a few more. Find the length of a chord that is a distance of 5 from the center of a circle. You'll need to draw and label your own circle. Now, here's the thing on these. How you draw your circle is important. So I'm going to draw a circle. Let me pick it up. I'm going to move it here. All right, and what I mean by, where are you going to draw your chord? The best place I find to draw chords is going right across the bottom so that I can see everything clearly. Now I know that here's the center, we'll call it R, the center is 5 from that chord. So I'm going to make the distance, the shortest distance, which I know would then be perpendicular, I'm going to make it 5. Now the circle has a radius of 8. So that means I can actually create a right triangle here and make that the radius of 8. So now I have a right triangle with 8 and 5, and I'm going to try to find x right here. Okay? Now, if it's the same, if a radius is equidistant, is perpendicular to that chord, then I know that these two segments are equal, and that will help me find the length of the chord. All right, so I'm going to have to use the Pythagorean theorem here. So x squared plus 5 squared equals 8 squared. And so then x squared plus 25 equals 64. Let me switch to black. Subtract 25 from both sides. Remember, whatever we do to one side, we have to do to the other. And I believe 64 minus 25 is going to give me 39. I'm going to take the square root of both sides. Remembering when I do that, you actually get plus or minus root 39. But because we're talking about length, we only have to look at the positive answer. So I know that this length right here is root 39. But I want the whole chord, and I have to double that. So I'll have to double that, which would make it 2 root 39. And there's the answer to the question. All right, we're going to try a few more. It says find the value of x and y. Okay, I see that these are equally distant right here, okay? That tells me that the chords are congruent, okay, if they are equally distant from the center. So I know that this chord is the same length as this chord. I also see that the chords are perpendicular, which means that the radiuses are perpendicular to the chord, which means it's being bisected. So x has to be 8, which then makes y 16. All right? So using these over and over and over again. All right, last one. This one's a little bit trickier. I see that these are perpendicular. But that's all I got. Well, that means that the chords are being bisected. So I know that this is 3 and this is 3, which makes this 3 right here. But I'm trying to find this length right here, x. So now this is where I have to use the idea of radius. I have to see if I have congruent triangles here. If this is a radius and this is a radius, well, I can do, it's a 3, 4, 5, which makes this 5 right here, which makes this one 5, which then makes this segment right here 4. So x would be 4, which means that they are equally distant from the center. Now, you might have also said, well, they're both perpendicular, so if this is being bisected, then this has to be 3. Just making sure that you're seeing all of the different ways that you can draw in radiuses to the corners of chords. All right, last one. I know it's a long video. Sorry, guys. It says sketch a circle P with a chord XY that is 10 centimeters long and is 2 centimeters from P. All right, so here I've got my circle. I've got my chord. I'm going to draw it along the bottom because it's going to be easier for me. It's got a length of 10. I have circle P, and I'm going to call that XY. It wants us to find the radius of the circle, but we know that this P is 2 centimeters from the chord, which makes it the shortest distance, so it is 2. It's perpendicular, so it's bisecting the chord, which makes this 5. And there's the radius, which I'm trying to find when I draw a line from the center to the end point of the chord. So again, Pythagoras can help. 2 squared plus 5 squared equals r squared. So we get 4 plus 25 equals r squared. 29 equals r squared. I take that square root again, remembering there's a plus or minus answer. So plus or minus root 29, but because it's a length, I only have to look at the positive. All right, guys, so those are some extra theorems on circles. I hope you have a wonderful day.